Welcome back everyone. In the previous video, we have discussed about Geschgorin theorem where we can identify the position of our eigenvalues. And now we want to determine our eigenvalues, and we can use the first method that you need to know is called power method. So what is power method? Power method is an iterative method that is used to determine the dominant, meaning that is the eigenvalue with the largest magnitude in absolute value form. And this is the definition. If lambda 1 up to lambda n are eigenvalues of matrix A such that the absolute value of lambda 1 greater than absolute value lambda 2 up to n, and hence, or meaning that lambda 1 is the dominant eigenvalue, that is the largest one. And we can use the power method that is given by the formula that I put in the box now. V k plus 1 over m k plus 1 multiplied by A v k vk, where our k start from 0, 1 and 2 and so on, depend on the number of the iteration. And then this is the step. First, we need to identify our initial eigenvector. And then we compute A multiplied by our first eigenvector. And then we can determine our eigenvalue m k plus 1, the largest in terms of absolute value. We want to find our m. And then the next, we compute what is the vector and then repeat the process until our stopping criteria is satisfied, or sometimes we use symbol epsilon. And once the iteration stop, then the dominant eigenvalue is approximated by the latest value. This is our eigenvalue. M is our eigenvalue, while the associated eigenvector is vk plus 1. So this is the step how we can find the largest eigenvalue. And we can put in a box, put in the table form, not in a box. And this is given the initial eigenvalue, and we must stop our iteration when mk, this stopping criterion is given. So let's look at example 4. This is the matrix given here is matrix A, and then we need to use the power method to compute the dominant eigenvalue lambda 1 of A and its associated eigenvector V1. And we need to use these initial eigenvector, and we must stop our iteration when the updated eigenvalue minus the second updated, which is must be less than 0.05, and we just use our calculation with 2 decimal places. So the first thing that we must do is to draw our form, and then we have our iteration k 0, and we have our vk, where v0 is given as 1, 0, 1. And of course, this is in terms of transpose. We already know. We know it. Bear in mind. And then after that, we have A, vk. And then we also have the column for m k plus 1. And then we can, let's say now we want to determine. So this is our calculation. At k equal to 0, we must find AV0, which is our A is 5, negative 1, 3, negative 1, 4, 0, 3, 0, 4. And then our V naught is 1, 0, 1. And then we can multiply this matrix. We can put this matrix in a calculator, and then we will have 8, negative 1, and 7. And then we can calculate our V k plus 1, so that we have our V1 is equal to 1 over the largest m, so that we have 8 is the largest, which is 1 over 8 multiplied by 8, negative 1, and 7, so that we can have 1 here, negative 0.13 and 0.88, like this. So before we calculate the eigenvector here, actually we need to determine our eigenvalue updated, so that mk plus 1, so that we have m1 is equal to maximum between absolute 8 and then absolute negative 1 and absolute 7, so that 8, absolute 8 here is the maximum, so that our m1 is equal to 8, and we have our eigenvector number 1. And then for k is equal to 1, again we need to iterate our calculation, or before that, let's put in the table here, so that we have AVK is 1, not 1, which is 8, negative 1, and 7. 8, negative 1, and 7. And our MK, the largest one is 8. Or we can look at here, so that here is column for mk plus 1 minus mk. Of course, for this one, when k is equal to 1, our v1, we know that is this one, 1, negative 0.13, negative, not negative, 0.88. And then we need to calculate. When k is equal to 1, AV1 is equal to, our A now is 5, negative 1, 3, negative 1, 4, 0, 3, 0, 4. And our V1 now is 1, negative 0.13, 0.88. If we put in the calculator, for this multiplication is 7.75, negative 150, 6.50, and implies that our largest, or M2, is 7.75, and then we can calculate our eigenvector. The updated one is 1 over m, the largest one here is 7.75 multiplied by our matrix AV1, which is 7.75, negative 1.50, 6.50, and then we have 1, negative 0.19, 0.84, and then Now we also can check our criterion, and minus M2 minus M1 is equal to absolute 7.75 minus 8 is equal to 0.25. And then you can put in the table here, we have 7.75 here, and then negative 1.5250, and then 6.50, and then our eigenvalue is 7.75, so that we have 0.25 here. And then when k is equal to 2, we have A, or we need to determine A multiplied by V2, so that we have 5, negative 1, 3, negative 1, 4, not negative 4, negative 1, sorry. Zero, and then 3, 0, 4, multiplied by V2, which is 1, negative 1 point, negative 0.19, 0.84. Then we have 7.71, negative 1.776, 6.35, like this. And the largest is 7.71, so that our M3 is 7.71 here. And then we can calculate our eigenvector number 3, so that it is equal to 1 over M3. Our M3 is 7.71 multiplied by A multiplied by V2, 1, negative 0.19, 0.84, and then if we do this one, we will get, I'm sorry, this one is 7.71, 1, negative 0.223, 0.82, and then we can put in the table, or we can calculate our M3 minus M2, which is 7.71 minus 7.75. You can get 0.04. And for the solution, it is less than, for the question, it is less than 0.05, so that we must stop our calculation. And then you can put in the table here. At 2, we will have this one, negative 1, negative 0.23, 0.82, 1, negative 0.23, 0.82. AVK, we have this one, 7.71, negative 1.77, 1, negative 1.77, and 6.35, I think. Yes. And then our M3 is 7.71 and is 0.04. Now we can stop. And our eigenvalue is the latest one is 7.71, while our eigenvector is the latest one, which is 1, negative 0.23, 0.82. So we can say that, therefore, the largest eigenvalue is 7.71, while the eigenvector number 1, or the largest one, is 1, negative 0.23, 0.82 transpose. So maybe when you do your calculation, you will see that the decimal places is not same like my answer, but it's okay. If you think that you are right, you can continue. Maybe my calculation here is a little bit wrong, because maybe at the beginning I put my decimal places is 4 or 3, but you can you try proceed, so maybe it will not different too much. Maybe for this one, for example, you will get 7.69, maybe. Please check. Okay, but this is how we use the power method to determine our largest eigenvalue for the given matrix. Now you can try this one. It is same one. Given a matrix A, and then you must use power method to compute dominant eigenvalue lambda 1 of A and its associated eigenvector V1, and this is your initial eigenvector, and you must stop your calculation when this dropping criteria is determined. And then now you must use 3 decimal places. Okay, you can try now. And that's all for now. Thank you very much for your attention.